Hey guys, hope everybody's doing okay. What we're going to do today is talk about our third and final law of thermodynamics, which is about something called Gibbs free energy. But before we get into that, let's revisit entropy a little bit and talk about, or at least think about, what type of substance would have an entropy value of 0, right? Which would mean no disorder whatsoever. So if you think about it, the only time that would really happen is when you have a temperature of absolute 0, or 0 Kelvin. So at 0 Kelvin, you may remember us talking about this in a previous chemistry class. At 0 degrees Kelvin, there is no particle movement at all, right? So you'd have no particle movement at all, which means you have really no disorganization and an entropy value of 0. So a crystalline substance at 0 Kelvin is perfectly organized. There's no particle movement, so there's really no disorder there at all. As you increase the temperature, though, what's going to happen? You guys know as you increase the temperature, particle movement starts to increase. So anything above 0 Kelvin, you're going to have at least some particle movement, and therefore you're going to have some disorder. So as the temperature increases, your particle movement increases, and therefore your entropy or your disorder is going to increase. So the greater the temperature, the greater the disorder, and the greater the entropy is going to be. This happens very drastically at a phase change. So if you have a solid, you guys know how particles look, and how they move in a solid. They don't move very much. They vibrate in place, basically. So there is some disorganization there, but it's not a whole lot. It's a relatively organized substance, right? But as that substance turns from a solid into a liquid, liquids are more free-flowing and there's less organization there, so it's more disordered, and therefore it would have a higher entropy value. Then think about liquid to gas transition. So gas particles have an extreme amount of disorder, right? There's basically no attractive forces between one gas particle and another one, so they are, since they're not attracted to each other, they're going off in all sorts of directions, right? And we know a little bit about our kinetic molecular theory of gases and how gas particles move. They basically move until they run into something, and then they move and they bounce off and move, and then they run into something else, and they just keep doing that. So there's a vast amount of disorder for gases and a great amount of entropy for that. We talked about that a little bit when we had our lesson on the second law of thermodynamics. Solids compared to liquids compared to gases. Gases have the greatest amount of disorder and the greatest entropy of the three main states of matter. So unlike enthalpy and overall energy, the S value or the entropy can be known, right? And you can just look these up at in a data table. So let's just look at the pattern or the trend here. You have liquid water at 25 degrees Celsius. The entropy value is 69.9 joules per mole Kelvin. So the unit here is really, really, really important. If you look at it, it is joules per mole Kelvin. If you think back to enthalpy, which is the H value, the unit on the enthalpy values you looked up was in kilojoules. Okay, so that is something that's definitely important to recognize here, so we don't make any silly mistakes. In a couple minutes here, where we're going to look at enthalpy and entropy basically at the same time in the same equation. We want to make sure that the units jive and they match up there. If you look at water as a gas at 25 Celsius, the entropy or disorder is 188.8 joules per mole Kelvin. So that's really important, again, to recognize that the gas state has more disorder and therefore a higher entropy value. Look at the next one. It's solid water, basically, obviously ice, at negative 273 Celsius. That is the same as 0 Kelvin, and the entropy value is 0. All right, if you look at the next one, that is methanol, CH3OH, as a gas, 237.6 joules per mole Kelvin. As a liquid, 126.8. You would expect that because a liquid is more organized, so there's less disorder. And then again, you have methanol solid at negative 273 Celsius, which is 0 Kelvin, and that gives us an entropy value of 0 joules per mole Kelvin for that. So you can see the two of them here at absolute 0, or negative 273 Kelvin, entropy values of 0 for both of those. Okay, something else I want to show you guys really quick when we talk about standard entropy is just this table that you guys have in front of you. And if you look at the end of your packet on the last page, you have a really big reference table, and the standard entropy values for many, many things are there. So we start with hydrogen gas, it's just H2. look at our entropy value. It's 130.6 joules per mole Kelvin. And as you get larger here, as you go from H2 to N2, we can see we have an increase in molar mass, so therefore we have an increase in entropy as well. And same thing with oxygen. It's even larger, so an increase in entropy there up to 205.0. As you get larger, we have methanol gas and then C6H6 gas. You can see that these have much larger entropy values for those as well. So in general, the greater the molar mass, the greater your entropy is going to be, and generally the more complex your substance is going to be, or the particle that you're looking at. And the graphic here shows you that trend. So let's take a look at how we calculate delta S for a reaction. This is really, really easy. We did the same strategy back in the Hess's law lessons that you guys looked at. So here's our chemical reaction. We have 3H2 plus CO2 yields CH3OH plus H2O. And it says, do you expect a positive or negative change in entropy? So we want to ask ourselves, is the entropy increasing or decreasing for this chemical reaction? So if you look at the reactant side, we have two gases. So it's lots of disorder. So high entropy value on the reactant side. Product side, we have a liquid and a liquid being formed. So it looks like this equation from reactant to product is getting more ordered. Okay? It's getting less disordered, right? So you got to think about what's the entropy change going to be here. If your entropy change is positive, you have more disorder. If your entropy change is negative, you have less disorder. Okay, it's a more orderly process. And that's what it looks like is going to happen here. Let's see if that's actually true once we calculate it, see if we're right. So if this equation looks familiar, it's because it is. Except instead of delta S, we're used to seeing delta H. So your delta S of your reaction is the sum of the number of moles times the entropy of your products minus the sum of the number of moles times the entropy of your reactants. So we can look all these up on our or in our reference table at the end of your packet. But I have a lot of those up here already, so you can copy them down. So your delta S, your change in entropy for this reaction, is going to be the entropy value from the back of your packet of CH3OH plus the entropy of H2O liquid. All right, there's 1 mole of each of those in the balanced equation, so they're just whatever they would be at the end of your packet. You're just going to pop those numbers in, minus the sum of all the entropies of your reactants. So we have 3H2 on the reactant side. So we have to subtract the quantity here. 3 times the entropy of H2 plus the entropy of CO2. So I looked a couple of these up for you already. And we have again, delta S of reaction as 126.8 joules per mole Kelvin. And we multiplied by the mole already, so it's really joules per Kelvin. Plus the entropy of water, 69.9 joules per Kelvin. We want to look up the entropy of H2 and multiply that by 3. So we'd have 3 times 130.6 joules per Kelvin, and then plus whatever it is for carbon dioxide, which is 213.79. So don't make a dumb math mistake, and you end up with an entropy value of, a change in entropy value of negative 408.9 joules per Kelvin. And it looks like that makes perfect sense. So the delta S, the change in entropy, is negative. That means we're getting more orderly, and there's less disorder. That's exactly what's happening here, going from 4 moles of gas on the reactant side to 2 moles of liquid on the product side. Okay? Let's see how this applies to the bigger picture here and the main idea for today. It says, which of the following would be definitely spontaneous at 25 Celsius? So we have to think of what's favorable here. What's thermodynamically favorable or spontaneous at 25 Celsius? You have to remember back to our a couple of our previous lessons on Hess's law and enthalpy. Delta H, you want that to be negative, right? This is actually from the last lesson on the second law of thermodynamics. We looked at the entropy and enthalpy relationship there, and what would be what would you need to drive the reaction forward and what wouldn't drive the reaction forward. So you want your delta H value to be negative for a thermodynamically favorable enthalpy. You want your delta S to be positive because you want disorder, right? A positive value is more disorder. You want a delta S value to be positive for a thermodynamically favorable process in terms of the entropy of that substance. So if you look at the list up here, reaction A, B, and C, we want to find one of them with a negative delta H. Looks like we have that right here. With a positive delta S. Looks like we have that right here. So letter B is the answer. That one will definitely be spontaneous at 25 Celsius. If you look at reaction A, we have a positive enthalpy value. So it's not really what we want, right? So that's kind of no good for the overall process. But remember, the overall process has to incorporate delta H and a delta S from that lesson we had on the second law of thermodynamics. The delta S value is favorable, okay? Because that should be positive. So this is good. Okay, this is not so good. So letter A is actually a maybe. Like, this might happen. We have to look at an equation to help us figure that out. We'll do that next. Letter C, oh, that's not what we want. You have a positive delta H value, so that's no good. And you have a negative delta S value, that's no good. So letter C is doesn't have any chance of being spontaneous or thermodynamically favorable. But A has a chance, right? And B doesn't, or B is automatic, right? Because your enthalpy and entropy are exactly the sign that you want it to be. So how can we tell for like letter A here, how can we tell if a depends situation, if a maybe situation would be spontaneous or not? A great example, and one that we could all relate to, is an ice cube melting. So you want to write the equation first. So you have H2O solid yields H2O liquid. That's your equation for the melting process. Now let's ask ourselves these questions. Does enthalpy favor this reaction? So what type of process is melting? Well, you have your solid block of ice. In order to melt it, energy needs to go into that, right? So we talked about this in Chem 1, and we've talked about it a few times in this class as well. This is a process that is endothermic. Okay, this is an endothermic process, and an endothermic process is a positive delta H, which is not what we want for thermodynamic favorability in terms of enthalpy. All right. So if it was just based on enthalpy, this wouldn't happen naturally. But sometimes an ice cube does naturally melt. Let's look at entropy. Does that favor this reaction? Well, H2O is a solid on the reactant side. H2O is a liquid on the product side. Are we getting more or less disordered here? Well, we're definitely getting more disordered because liquids have more disorder than solids do. So this looks good, right? So the thermodynamic favorability of enthalpy is not favorable. The thermodynamic favorability of entropy is favorable. So this is one of those depends or maybe situations. The spontaneity or thermodynamic favorability of this reaction depends on what? Well, it depends on if it's cold or not, right? So if you're in the middle of winter and it's freezing cold outside and the temperature is below 32 degrees Fahrenheit or 0 Celsius or below, then this is not going to be a spontaneous process, right? The ice will remain there until the temperature goes back up. If the temperature is above 32 Fahrenheit or 0 Celsius, then yeah, this will be a spontaneous process. Okay? So if you have a depends or a maybe situation, the spontaneity is going to depend on temperature. Let's see how that works in the next couple examples here. So here's what spontaneity was going to depend on. 3 things. Change in enthalpy, change in entropy. So we have delta H here, delta S here. And if delta H and delta S are favorable, then who cares what the temperature is? It's going to happen all the time. If delta H and delta S are both unfavorable, it doesn't matter what the temperature is. It ain't going to happen. But if one of the two here, okay, if delta H or delta S is favorable, there's a chance, and it's going to depend on temperature. So the only time it's going to depend on temperature is when you have either delta H or delta S favorable. Not both. All right? So again, both are favorable. It's good to go. No one cares what the temperature is. If both are unfavorable, we're not good to go. Doesn't matter what the temperature is. But if one is, we have to look at the temperature. So here's where Gibbs free energy comes in. It's our new term for today. This refers to the amount of energy available to do work. All right? So it's kind of hard to understand this, but you want to think of it as how much free energy is available once you take in enthalpy and entropy and see how they work together. All right, so here's our equation. It's delta G equals delta H minus T delta S. That's extremely important. You're going to use it for the rest of the unit. It's really easy to understand in my opinion. So take a second to write it down. And then let's focus on this question here, which is really, really important. What will the sign of delta G be on a reaction that is definitely spontaneous? This is a huge, big idea for what we're talking about right now. You want, for a definitely spontaneous reaction, the delta H is negative, right? Your temperature is in Kelvin. It has to be above 0 because 0 Kelvin is the lowest you can go, right? So you know your temperature value is positive here. It'll always be positive. And then look at what your delta S value has to be. If you want something that is definitely spontaneous, remember your delta S, your entropy, we want to be positive. Okay? So if you have a negative value here for delta H minus, if temperature and delta S are both positive, you're going to subtract a number, right? So a negative value minus a positive value, you're going to get, no doubt about it, a negative number, right? A negative number minus another number is just going to be more negative. So delta G is negative for spontaneous or thermodynamically favorable reactions. Okay, write that down. I know it's on your note sheet somewhere. I'm looking right at it. That's what we need to write down and need to know here. All right. So delta G is negative for a spontaneous reaction. So if you know your delta H value, you know your delta S value, you can plug them in, of course, and your temperature, and whatever you get for delta G, if it's positive, it is not spontaneous. If it's negative, it is. Okay. So here are our three general rules. I kind of just summarized them for you. But if delta G is negative, the forward reaction is spontaneous. If delta G is positive, it's not spontaneous in the forward direction, so it'll be obviously pushed as much to the left as possible here, so it won't progress forward at all. And if delta G is actually 0, then the system is at equilibrium. Okay, so we're not done with equilibrium yet. I mean, we mostly are, but it comes back here and there, and this is an example of that. So let's go through this question here. Which of the following would be spontaneous at low temperatures but not at high temperatures? Let's go through the list here of delta H and delta S's and see what we get. Okay, so remember our delta H, a favorable delta H value will be negative. A favorable delta S value will be positive. Okay, so let's go through and just see, are any of these going to be spontaneous regardless of temperature? So we need a negative delta H and a positive delta S. That looks like letter B. All right, so letter B will be spontaneous no matter what. Okay, which one won't be spontaneous at all, no matter what? So if something has no chance of being spontaneous in the forward direction, we need a positive delta H and a negative delta S. That looks like letter A. All right. So letter A has no chance of being spontaneous no matter what temperature you're at. So we're down to C and D. Okay. So in order to figure this out, we need to look at our delta G equation, our Gibbs free energy equation. So delta G equals delta H minus T delta S. Okay. I'm going to erase the spontaneous word here in case I need to do a little bit of scratch work for you. Okay, so we're looking at C and D. If you look at letter C, we have a negative value for enthalpy, so that's good, right? And we have a negative value for entropy. We want it to be positive, so that's not good. So this is one of those situations where it's a maybe, right? We have one of the two things, in this case delta H, favorable, and the delta S isn't. So you want to ask yourself, we want something to be spontaneous at low temperatures, all right? So let's look at the equation up here, and let's just plug in, like you don't need to officially solve it because you don't know what temperature you have, so you can't actually get a delta G answer here. But you could plug in negative 42 kilojoules for delta H. So let's say this is a negative number right here. All right, let me find a better spot to put this. It's still not great, but it's okay. So delta G is, or delta H for letter C is negative minus T. Then our delta S is positive, okay, or is negative. It's negative 18. So it's negative. All right. So here's the deal here with this. We want the delta G value to be negative. Like we want delta G negative for a spontaneous reaction. So enthalpy is working in our favor here. Okay. We have a negative number, but if we do a negative number minus temperature times your delta S will give you another negative number. Right? So if we have a negative number minus another negative, this will turn out to be some negative number, you know, your negative 42 kilojoules for delta H plus something. We don't want that number here to be big, right? Because if this number, that squiggle, okay, if that number is really big, then the delta G ends up being positive, right? Which is no good. So we want our temperature to be as low as possible here, okay? If our temperature is as low as possible here, it keeps that squiggle I have, it keeps that value really small. So a negative number plus a really, really small number gives you a better chance of retaining a negative delta G value. So C is the answer for that, okay? If we had a high temperature here, if this T value, that temperature is really high, then it's going to make this squiggle here a really, really big number, okay? So you'll have a negative plus a big number, and that'll give you a positive delta G value, okay? If you look at letter D gives you a positive delta H value, which we don't want, but we have a positive delta S value for letter D. So that's okay, right? So let's see what would need to happen here. So delta H is positive 42, that's fine, minus T, and then delta S is a positive value. Okay? What we want here for delta G is obviously a negative value overall. Okay? So what we want here, we have a positive value for delta H, positive value, minus T times a positive value. So you're going to be subtracting another positive value here. You want this value, that squiggle, to be really big, right? If you have a positive number minus a big positive number, like 42 minus 300, you're going to get a negative delta G. So for letter D, you really, really want a high temperature because that'll make this value here big, and therefore your delta G value negative. Okay, it's a little confusing because I'm talking through it without like a temperature value here. But once it's just simple math, right? If you're just adding or subtracting numbers, you want to figure out what could you do to get a negative delta G. End of story. That's what you want to get. All right. So here's a quick little key for this, where you have what's your delta H, what's your delta S compared to the number 0? Is it positive or negative? And then when is it favorable? You may or may not appreciate this, but I'm going to teach you a thermodynamic favorability dance when we get into class one day, and it helps summarize this, so be prepared. So for the delta H, if it's negative, it's less than 0. So if it's negative, and the delta S is positive, That's what we want, so it's favorable at all temperatures, spontaneous. If the delta H is positive and the delta S is negative, then it's not favorable at all. It's not spontaneous, so no temperatures, doesn't matter. If the delta H is positive, which is what we don't want, but the delta S is also positive, then high temperatures are where we need to be. We just did an example like that in the previous slide. If the delta H is negative, that's good. If the delta S is negative, that's bad. We want low temperatures, and we just talked about that. So you want to try to think about this, right, and kind of know what those different situations are. I don't memorize any of it. All I know is that delta G has to become negative, okay? And in order to get a negative delta G value, what do I need to do here and here? Or what do I have there? What does my temperature need to be? All I do is some simple math calculations, some simple addition or subtraction, and go from there. So to wrap this all up here, I have a couple examples of equilibrium. So if you have PB solid to PB liquid, that's melting, that's a phase change. The equilibrium during this melting point is occurring, so the delta G will be 0. For the one underneath it, you go liquid to gas, you're boiling, or going through that phase change of liquid to gas for water. So you're at equilibrium during that phase change, so the delta G will be 0. So it's really, really important to understand that when you're at equilibrium during a phase change, your delta G value is 0. That's really important for some of the practice problems we're going to eventually do here. So make sure you make a note of that on your note sheet about delta G being equal to 0 at equilibrium. So therefore, when you use, therefore when you use this equation here, if you're at equilibrium, like for this lead example, solid to liquid, delta G is set equal to 0 because it's at equilibrium. You could figure out your delta H and delta S by looking them up. If you solve for T, guess what? You just figured out the melting point for lead. Same thing with this one. You could figure out the boiling point of water. If you set delta G equal to 0 because it's at equilibrium, look up delta H in a reference table, delta S in a reference table, solve for delta T with your algebra, and there you go. You have the boiling point of water. Okay, here is our last problem for this lesson. And this is the last big main lesson of the unit. There's a small one after this. It doesn't take too long. But here's my practice problem. I want to use the following information to determine the boiling point of C2H5OH. This is basically just what we talked about in the previous slide. So I want to set up my equation, delta G equals delta H minus T delta S. I also want to have my equation for what's happening in this chemical reaction. So I think I have that pop up here for you. So I have C2H5OH liquid yields C2H5OH gas. So you want to write that down. And I need to use my Gibbs free energy equation because it has the temperature value in there. And that's going to help me determine if, or it's going to help me determine what the boiling point is. I'm going to solve for that. So I'm going to rewrite it down here. Delta G equals delta H minus T delta S. I want to set my delta G equal to 0 because I'm going from liquid to gas. This is a phase change. This is boiling. And on the previous slide, if you have a phase change, you're at equilibrium, delta G is 0. That's equal to delta H minus T delta S. If I reorganize this equation, I move delta H over here, okay, negative delta H equals negative T delta S. The negative signs cancel out and divide both sides by delta S. I end up with delta H over delta S equals T. That is what I want to use to solve this. Okay? So what you'll end up doing here is figuring out what is the delta H for this reaction and what is the delta S for this reaction. Okay? So if you go back to one of the earlier slides here, your delta H or your delta S is always found by doing the product minus the reactant. So my product is C2H5OH gas. So to find the delta H, I need to take the enthalpy of C2H5OH gas as a product here. So it's negative 235.1 kilojoules per mole minus your reactant, because it's always products minus reactants. So I look it up, it's minus negative 277.7 kilojoules per mole. And if you figure that out, you get an answer of 42.6. All right, so that'll be 42.6, and that's going to be kilojoules, all right, per mole of reaction. Do the same thing for delta S. All right, if you do the same thing for delta S, you take your entropy value of C2H5OH gas to 82.6 joules per mole Kelvin minus 160.6 joules per mole Kelvin. You get an answer of 122 joules per mole Kelvin for the delta S. That's a problem because if you look at your delta H, it's in kilojoules. So there's that discussion about units that we had in class and earlier on in the unit here, where it's really important to include units in your calculation, so you don't make a dumb mistake of just saying, oh, one of them is 42.6, one of them is 122, I'm good to go. You're not good to go because you need to convert 122 joules into kilojoules. So just multiply by 1 kilojoule over 1,000 joules. Once you do that, you get 0.122 kilojoules per mole Kelvin. All right. Finally, you want to actually plug that into your calculator. 42.6 joules per mole divided by 0.122 kilojoules per mole Kelvin. The kilojoules per mole and the kilojoules per mole cancel. You're left with Kelvin as your temperature, and you get 349 if you go to 3 sig figs. All right. So the boiling point of this is actually ethanol. The boiling point of ethanol is going to be 349 Kelvin based on this. So it's pretty simple actually. You can reorganize the equation. That's simple algebra. And then it's just a matter of not making the silly mistake, all right? Keeping your units under control, recognizing enthalpy is in kilojoules, and your entropy is in joules. If you look at your reference table at the end of your packet, the only thing that's in joules is entropy. Enthalpy is in kilojoules, and Gibbs free energy, delta G, is in kilojoules as well. Okay, that takes care of it. That's the third law of thermodynamics for the most part. We'll do some practice problems in class, and we'll go through some of this stuff. This is the main lesson for the unit. We have one more small one after this, and then we're good to go. All right, thanks, guys.